And here we go. All right, guys. At least I can see myself. It's not so lonely. Okay, let's start the lesson. Let me share the screen quickly. So today we are going to learn about nuclear collectivity, about collective motion. So let me make this bigger. So we are going to talk about let me go here, about nuclear collective motion. So yesterday we learned about how this particle, that we have two particles in the 0 p 1/2, right? And these guys are normally coupled. And then we have one extra particle here in the 0 d 5/2. And then suddenly we broke a pair, right? And we promoted this guy here. So in a way that this guy now form a pair, and this guy actually is not there anymore, right? So the odd particle was this one, and this happened for 15 nitrogen, right? Or to explain the J pi equal 1/2 minus that we have for this nitrogen 15, and I have it here somewhere. So nitrogen 15, the ground state, as you can see, is 1/2 minus. But also we explain some excitation in oxygen 17, and hopefully you went to the NMDC and check what is the situation with oxygen 19. So did you do that, guys? Did you go to the NMDC and explore what is the situation with other nuclei? So this is a must do for the test, the online test. You go to the NMDC and see, you see oxygen 19. We went through fluorine 17, 21 neon. Always, as I say, odd even nuclei, where you have an odd number of protons or neutrons, right? And the other one is even. So these excitations here, we call them single particle excitations, and the reason is clear because they just involve the promotion of the excitation of one particular particle going up. Before we said this could break, and also they could go up there. But these are basically single particle excitations because we promote one particle or even a few particles. But I want you to look at the NMDC online and check what are the ground states. So what are the ground states? Let's write it down here so we just have a little bit of space. What are J parity for ground state and first excitations in those nuclei, right? In some, in a bunch of nuclei. Just check yourself any possibility that you want to investigate, but remembering that you need to have a not even nucleus, right? Like here we have 10 and 11. All right. So these were single particle excitations, and now we are going to treat. We're going to go to the nuclear collective motion, and we are going to see that the nucleus actually may take a shape, and it may rotate, right? It may rotate like this and have a motion like that, a rotational motion, right? And the nucleus normally have a symmetry axis, which we're going to call Z, and this is called a quadrupole shape. And this collective motion we have already investigated when we went through the harmonic oscillator. So in the harmonic oscillator, you have the main oscillator quantum, which is n equals 0. As you remember, n equals 0. We have, and then there was always a h bar omega energy difference between this one and the next harmonic oscillator quantum number, then the next one, right? But then how does this translate? And we call this collective vibrations, and the nucleus itself can vibrate and can rotate. So our ground state, here we go for a nucleus where I know we are studying right now, nickel 60. We ran this experiment before COVID, and 2 master students are analyzing this nickel 60 for nickel 60 and nickel 62 actually. So then it will have a ground state of 0 plus, because we have even numbers of proton and neutrons, so they couple with each other, and then they couple to J equals 0. So the ground state is 0 plus, right? Then it's going to excite to a 2 plus, and then it's going to de-excite emitting a gamma ray. 2 plus is and we call this is the one phonon state. So the phonon takes 2J equal 2 units of angular momentum, 2 h bar. Remember, the units are always in h bar. And then we have another level here, which will be excited through another phonon, and this guy would have, with a 0 plus, become a 2 plus, we have a 4 plus, and we call this fellow a 2 phonon because it's vibrating, and the phonon is the quantum quantity which measures the vibrations in the microscopic world, not only in nuclei but also in material science, molecules, and atoms. These are 2 phonon, and again there's as you can see, again here we have the same kind of energy, the same. So the characteristics of these vibrations is that the E, say the E of the E4, let's call it the energy of the 4 plus this one. This is the energy of the 2 plus here. So basically the energy of the E4 divided by the energy of the 2,4 is going to be equal to 2, right? So this is the characteristic and arises from the harmonic oscillator, right? The harmonic oscillator has equidistant energies, and so our nucleus, our vibrating nucleus, we have a similar, this state will be degenerate, and this is the coupling of the next phonon with this 2 plus state, which will produce this 0, 2, and 4, these 3 possibilities. And ideally, these are degenerate, which means that they have the same energy, right? In reality, this is not the case, and but this is a matter of different of going deeper into the subject. So for our particular case, we want to know that this ratio is the ratio for a nuclear, let's call it vibrator. Okay. How does this vibrator would look like? So this will be the excited by gamma rays, right? You excited through the phonon states, and then the excited by gamma rays. So in a typical spectrum, we have where here we have here we have counts, and here you have calibrated it in let's say in kV. So we will have a typical spectrum which would look like this. So the energy of the peak from the 2 plus to the 0 plus will come here, right? But this is 2 times an excitation, but the gamma rays are the same, right? So then there will be another gamma ray with about the same energy, or almost with the same energy right there. So this will be the transition from the 2 plus to 0 plus, which generally is bigger than this one. And this will be the transition from the 4 plus to the 2 plus. So basically, and also we have the transition from the 0 plus to the 2 plus, 2 to 2. So basically, we will see in an ideal vibrator, we'll see just one peak right there. And ideally, there won't be no separation, but truly we see a little bit of separation between the peaks. And this will be the characteristic of a nucleus vibrating. The energy of this 4 plus to 2 plus is 2, the ratio. But when you look at the spectrum, like you do in the pracs that we run in our lab, right? When we look at the spectrum, this will look like we have 2 peaks or 3 peaks together. Actually, 0, 1, 2, 3, and 4 peaks together, right? 0 to 2, 2 to 2, and 4 to 2, because this energy is the same energy as this one, right? Although the excitation energy is different to the gamma ray energy, right? So here we always have the energy of the gamma ray. This is what we detect in our spectrum, right? So similar gamma ray energies for the nuclear vibrator. If we see this happening, this will be a clear case that we have a collective vibration. All right. So this arises, as we know already, from the harmonic oscillator. So now, now we're going to go to another collective rotations. Another mode of collectivity, which is the collective rotation. So, for instance, I didn't mention that before, but generally these are energies of 1 to 2 MeV for these oscillations, right, or vibrations of the nucleus. So basically, the nucleus can oscillate around, the surface. These are called surface oscillations, and obviously this also 1 to 2 MeV energy difference, right? And these surface vibrations of the nucleus should lead to this kind of situation, which in the spectrum it looks like one peak basically over superimposed, because there are 4 peaks about the same energy, right? So this will be the signature for a vibrator. So now, what happened with in rotation, the nucleus take less energy to rotate. So this, instead of 1 to 2, you may have a few kV. So the nucleus will rotate with a particular pattern that we're going to investigate right now. But the energy of rotation is much less, around, let's say, 50 kV. So the nucleus needs less energy to rotate than it needs to vibrate. And how do we know this? And we're going to explain it right now. Because let's assume a rigid rotor. A rigid rotor, the distance between particles, this is a typical molecule or whatever, coupled with so this is L. So the distance here is always the same. So the characteristic of the rigid rotor is the potential energy is equal to 0 because the distance between particles is the same. So basically the energy total is equal to T plus V. V is 0 and T is equal to, in a rotation, remember, for a translation, we have that T is equal to 1/2 of mv squared. But for a rotation, we have that T is equal to 1/2 the m changed by the moment of inertia and v changed by the radial velocity, right? As we know also that angular momentum is equal to the moment of inertia times the radial velocity. So we will have that omega is L squared over I squared, omega squared. So we have L squared over 2 times the moment of inertia. And obviously this will be the total energy, L squared over 2 times the moment of inertia of the rigid rotor. Now we can apply quantum mechanics once we know the energy, total energy. We can apply quantum mechanics and say, okay, we are going to get the eigenvalues, and for that, let's say L, remember L is characterized by L squared and LZ. So we're going to have L m here with the wave function. And the wave function will apply as L squared. So it will be 1/2I L squared of Lm, which will be h bar squared L plus 1, 2 times the moment of inertia, Lm. So the energies will be equal to Lm h bar squared L plus 1, 2 times the moment of inertia, Lm. And because of the orthogonal property, Lm is the same as Lm, which is equal to 1. So basically, we have the energy of the rotor, which is given as h bar squared over 2 times the moment of inertia, L plus 1. Okay. And this is, as we know, the same rules apply for L, for J, for S. So this actually we should have said is J, the total angular momentum. And we're going to investigate the possibilities that arise from this calculation that we just did. So for collective rotations, let's write it, collective rotations, we have proven that the energy of the rotor, which depends on J, we're going to call it J now, is h bar squared over 2 times the moment of inertia, J plus 1. For J, as we know, is the total angular momentum. Defined as, J equal L plus minus S. Or capital L and capital S. Right? So now we are going to investigate, and we're going to see how the energies of a rotor look like. What are the excitation energies of this rotor? So then we're going to investigate. I'm going to say, okay, we're going to assume that we have a nucleus which is rotating, and we're going to draw it here. So we have an even nucleus, let's say 178 hafnium. As it is even, the ground state is 0 plus. And then each photon energy, we have a jump of 2 h bar for a rotation. So the energy of the 2 will be equal to h bar squared, 2 times the moment of inertia, 2 plus 1, 3 times 2, 6, right? So now let's do the same thing for the 4 plus E4. So we're going to have a 2 plus here. And let's call it this, assume this 50 kV, as we assumed before. And now we have for the 4 plus, we have the h bar square over 2 times the moment of inertia. 4 plus 1, 5 times 4, 20, right? So then obviously this is going to give us a E4 plus to E2 plus ratio, which is going to be equal. We're going to assume that obviously these guys are going to cancel if they have the same moment of inertia. We are assuming here that we have a nucleus rotating as a whole. And then we have these excitations that we're going to investigate, how the nucleus excites when it is rotating, right? So then this will be 20 divided by 6, which is equal to 3.333, right? So here we have that if this is 50 kV and we multiply by 3.33, right? So we will have that 50 multiplied by 3.33 is going to be equal to 166.5. So 166.5 is somewhere here. We can make it easier and then say, let's say 100, and this will be 333, right? But remember now that the energy of the gamma is always the energy difference between 166 between the two states, right? It's not 166, the energy of the gamma, but it's the transition between this level and this level, right? So it's 166 minus, so the energy of the gamma will be 166 minus 50, right? And this is what we will see in our spectrum. So we will have a peak, counts energy in kV. So we have the first one, which will be a peak at 50, because here the energy difference is the same, right? And then we have a peak at 116.5. This will be here 116.5, right? This will be 50. And these are the gamma ray energies depopulating these guys. And now we want to see what happened. For instance, we can do the same thing for the 6 plus, right? We can say that the energy of the 6 plus will be equal to this is the general formula right here. So the energy of the 6 plus will be 6742. So will be h bar square over 2 times the moment of inertia times 42, right? So then we can play the same game and say, when is the next level coming here? What is the 6 plus coming? So the 6 plus over the 4 plus or whatever, over the 2 plus, over the 2 plus, let's say, the 6 energy of the 6 plus, let's write it down here. Energy of the 6 plus divided by the energy of the 4 plus or the 2 plus is just a reference. So that will be 42 divided by 6, right? 42 divided by 6 will be equal to 7, right? So basically, this 6 plus here will come up there at energy, which will be 7 times 50. Basically, 350 kV. Right? 7 times 50, 735, 350 kV. But the energy here, it will be 350 minus 166, it will be 184. So the energy of the gamma will be 184. So in this spectrum, we have a 184 energy right here. And we can continue. And this will be the energy of the 8 plus, the transition from the 8 plus to 6 plus. But I will leave it here for you to again explore. And what is the best way to exploring this thing? Is just to calculate. We have the total energy of the rigid rotor. We don't have potential energy because the particles they always keep the same distance. The distance is fixed. So we are going to the here, and this is a typical spectrum of, you go to 228 h bar. You go up, and the nucleus keep moving in units of 2 angular momentum, right? Keeps being excited, and then here you go up to 60. So you have all these gamma ray energies, and you can see the particular pattern is that now it seems to have equidistant gamma ray energies, right? Before, remember, we have equidistant levels for the harmonic oscillator, but one property of the rotor, the nuclear rotor, is that we have equidistant gamma ray energies. So now let's see whether this picture that we have concluded here makes sense. We have used classical mechanics. We have quantized the rigid rotor, and we have inferred the energy levels. But then let's see whether this ratio of energies actually make any sense or not. So we go to our ENSDF, and the nuclear mass 180 is well known for being well deformed. And this is important for rotations to happen. For rotations to happen, you need to have a well-deformed shape to have a projection onto the z-axis, right? If you don't have any LZ, you won't have any. You have a sphere. You imagine a sphere. I'm actually going to show you, and you. Here we go. You take a sphere like this one, and you rotate it like this. See, if you project this onto the whiteboard there, right? The shade of the shape onto the whiteboard. Let me see here. If you project this onto the wall or the whiteboard or whatever is there on this side, if I rotate it like this, it won't project because you won't see any rotation really happening. So for rotations to happen, you need to have like a rugby ball, right? Where you have an elongation, and then you will see in the projection, if you flash a light onto the rugby ball, you will see that the shade actually is changing, right? The change in the shape is telling us that the rugby ball is rotating. But a sphere rotating doesn't rotate. In quantum mechanics, you cannot see. You cannot see a sphere rotating because what I just mentioned. There's no projection. There's no change in the shape in the projection of the basketball, for instance, right? So we are going here 178 say hafnium. This was we select all, and we're going to put it here in documents, lecturing, quantum mechanics 221, 178 hafnium, and DC. 178 hafnium DC. And we're going to open it right now. I want to see how things look like. So let's see. let's write it down. The ground state is 0, but remember, this is just a reference. There's never a 0. The real energy of the ground state is the binding energy that we can calculate. I mean, we know that this energy is negative because it's deep into the potential, right? If there's no 0 energy in quantum mechanics, but just as a reference, let's write it down like this. And we're going to our working board here. And we're going to see what happens. So we have the ground state of is a 0 plus, 0 energy, 178 hafnium. This comes from the NDC. Basically, this is the experimental values, right? This comes from experiment, and we see that the 2 plus energy for the rotor comes at where are you guys? Here, at 93.2. Let's say 93.2. Let's call it 93. 93 keV. Okay. So the next level comes is a 4 plus, as you can see here, at 307. Let's call it 307. 4 plus comes at 307 keV. The next one comes is a 6 plus, comes at 632. Comes up there at 632 kV. And then there's another one. It's an 8 plus, which comes at 1058, right? This one right here. So this one right here at 1058, 1059. So it goes up there. We're not going to, well, let's write it down. An 8 plus here at 1059. And now let's apply our model, right? We have a 2 plus, a 0 plus, and this is 93 keV. We are going to assume this is the energy or the first 2 plus because as from an experiment. But let's see whether our rotor, our energy of J equal h bar square over 2 times the moment of inertia, J plus 1. What does it bring us? Okay, so 93 keV. We know from before that the energy ratio of the 4 plus to the 2 plus is equal to 3.33. So according to our model, the 4 plus here, this is a 4 plus, will come at 93 times 3.33, which is equal to 309. So according to our quantum mechanics model, this should be the energy. And then the 6 plus will come here. And we have also deduced a formula for the 6 plus. Here, the 6 plus to the 2 plus, the ratio is 7. So the energy ratio of the 6 plus to the 2 plus is equal to 7. So 93 times 7 equal to 651. 651. So as you can see, and then the same thing will happen, very close energy. As you can see, our model, this is reality, real, a model, our rotor model, is predicting quite nicely the energies, and this is not the best rotational case. I just shows it, but you see the energy 632, 651. We can also get the energy of the 8 plus over the energy of the 6 plus and see what is the ratio here and see what's coming here. And I leave this for your exploration. And I leave this for, there are other nuclei, which may be better rotors, but you can see that our picture, our very simple picture, remarkably matches the energies within a few keV, right? Between the real experiment and the model. So one of the things of the moment of inertia, for the rigid rotor, for you just to keep in mind that it's not really what the moment of inertia that we find experimentally. It's about 2 times the moment of inertia that we find experimentally. And the rigid rotor, the motion of the nucleus going as a rotation, going like this, is also called the rotational flow. You can find this rotational flow. Basically, because these are these guys won't really remain static. There will be a flow of the rigid surface, the rigid body going in this rotation. So as you can see, we have done a little bit of magic here, and from a classical point of view, we have deduced what the nucleus will look like if we have a rotor. So there are many other things that we can investigate, and we can investigate what are the perfect rotors. We can go through the books and maybe say, okay, here we go. Let's investigate, for instance, any in the mass 180 will look similar. I'm sure there's a nucleus will looks much better than what we have calculated right now. We have chosen 178 hafnium, but we could have chosen something more closer to our rotational picture, right? So like this Prosium 158 or some of these nuclei, which are actually very, they look also rare earth. So the mass 180 and the 150 something, Samarium 158. Let's look at this. Let's look at this for a little bit. Explore which nuclei are more rotational than others, if there's such a thing. Let me see. Here we have, that's the PDF. I want to go to the online here. So I don't know if there's any. So basically, the lower the energy, E2 plus energies in nuclei. Let's see if there's any plot like this. The lower the energies of the first 2 plus, the more, the better will be the rotor. You can see here. I mean, you have lots of examples, and but basically that's it. I mean, you have to explore in the NDC. I think I have it here in one of the. Let's investigate another one. We just have to investigate another one. Let's say we go here and we choose samarium 158. And let's see how it looks like. There's not many, so that's not very well known. Let's say samarium 156. And select all. Let's see how this one looks like. 156 samarium NDC. And again, you go and do the same process as we have done ourselves. This looks a little bit better because you see the energy is a little bit lower. So let's assume again this is 75, and let's see how it looks like. Let's see now whether we can predict ourselves what will happen. So we have the 0 plus, we have the 2 plus, and this is 75. So without looking at the NDC, we know that the 4 plus will be 3.33 times that, 75 times 3.33, which is about 250, right? 250 kV here. And now we look at this is what for samarium 156, we say. Even nucleus, 0 energy here, kV here. And let's see what happened in the NDC. NDC actually 250, boom, match 100%, you see. What will be the energy of the next one? According to our model, we know that the 6 plus, we have a factor of 7, the energy of the 2 plus. So 7 times 75 will be equal to 525 here. 525 kV, where again, we're just applying our rotor eigenvalues for the rotor as to h, here we go, j plus 1, right? We're just applying this that we extracted from T1/2 of I omega square, right? From the kinetic energy. So then 525, what is the next one here? 517, okay, so almost there. So the next one we can also calculate will be an 8 plus, the next one will be a 10 plus, which is here, always in units of 2 angular momentum. The next one will be a 12 plus, and there will be other things, as you can see, but this is not the purpose of this lecture. All right, I want now we're going to stop. I want to see if you have any questions.
Prof, I just want to ask, are you saying that the energy levels move in multiples of 2, like 0 plus, 2 plus, 4 plus, 6 plus, and so on?
Right. The energy levels for a rotational band, it will always go in steps of 2 angular momentum, right? 2 units of angular momentum. Where the first one is a 0, obviously, and then 2, 4, 6, 8, 12, up to, as we saw at the beginning, up to 60, right? H bar.
Okay, and I see with here, so the parity will never change in this case. We'll always have a positive parity.
Right, for the same rotational band. So let me, for the same rotational band. So this is a very important concept. If the nucleus is doing the same, the parity won't change. So tomorrow we're going to see that the nucleus here in the this is what we call this rotation. Let's say this is the ground state rotation. So in the ground state, the nucleus will have a 0, a 2, a 4, a 6, 8, and we'll continue up to very high units of angular momentum, 60. So, and these guys will all decay, and obviously the multipolarity will be an E2, and the way it looks like is one peak, another peak, another peak, another peak. It's important that we see when we look at to the lab, the energy of the gammas in kV, right? This is the counts. We know that this particular pattern of similar equidistant gamma ray energies it means that this guy is rotating, right? is getting excited by rotation. But tomorrow we'll see that suddenly, remember before in the shell model, we say that, okay, we can have a pair of particles and they break. The same thing it may happen here. We have a pair of particles and they break, and this pair of particles go around the nucleus. And then these guys are not doing the same as these guys. So all these guys are doing the same thing. The nucleus is doing this. And hence, the wave functions will look very similar. All the wave functions will look very similar. And they will decay very fast because the transition probability.
Which wave functions? Are you showing us something or?
So these are each state has a wave function, right, Songesu? So
are you showing us something?
Oh, okay. Sorry. I stopped sharing, no? Right. Actually, I was showing you something. Thanks, Songesu. Chat, not always. It's just one. I just chose one possibility to divide by the 2 plus. Obviously, for the 4 plus, you need to divide by the 2, but for the 6, 8, you can divide by the 4, the energy of the 6. But then the ratio must, is according to the energy that you are making the ratio, right? It doesn't need to be the 2 plus.
So how can it be the energy levels, bro? Like, is it, for example, between 4 and 2, and then 6 and 4, and 8 and 6? Does it work like that?
You have this formula, right? H bar square over 2 times the moment of inertia, J plus 1, right? So the energy, you can make any ratios. Energy of the 8 plus with respect to the 4 plus, it will give you an energy ratio. So you basically, if you have the 4 plus here, you know where the 8 plus will come, right? Because it will come, if you have whatever, 7 or 8 or whatever is the number, 7.5. So this energy will be 7.5 of this energy, right? So it doesn't need to be the 2 plus. It can be any energy that you choose.
Okay, thank you.
Prof, I just want to ask, since for the 0 plus angular momentum, we have a 0 energy, how do you determine the 2 plus then? Is that something you just have to know that it's 93, then from there you can start using ratios of 2?
So yeah, because this energy, as we saw before, for half nu, it was about 95, right? And for this Siberian 156, it was about 75 kV. So it's going to be in this order, but it depends on how well deformed the nucleus is, right? And we don't know that a priori. So we need to actually determine what is the elongation, the quadruple deformation. The quadruple deformation of this fellow. And depending on how well deformed it is, the more deformation we have, the easier it will rotate, and the lower will be this energy, right? So, but that we don't know unless we see at the energy spectrum. So the energy of the 2 plus will be always a given, because we don't know what it is, what is the shape of the nucleus before. So we need to have at least one energy to refer to, right? Is that clear?
Yes, thank you, Prof.
So the energy of the 2 plus will be a given, because this energy is crucial, because we don't know how good of a rotor this nucleus is unless we see the energy here. As we saw yesterday for oxygen 17, right? There was a 1/2 plus here. There was a 5/2 plus here, and then there was a big jump of 3.06 MeV for the 1/2 minus, right? Because this 1/2 minus involve the breaking of a pair and the promotion of that particle through the magic number 8. So these energies are depends on the distance, the separation between these single particle orbits. But these are single particle excitations, as opposed to these ones which are collective excitations, right? So very important, the nucleus, as soon as the nucleus is doing the same thing, the wave functions, they're just drawing here, whatever, the wave functions will look the same. And therefore, a transition between a 2 plus through an E2 transition, remember these are all decaying by E2 transitions, through an E2 operator to the 0 plus, or the transition from the 4 plus to the E2, 2 plus, there will be large values for this overlap between the wave function of this guy and this guy, because these two are looking very the same, right? This is what is called the transition probabilities. That now, and these are the things that we see here. This is going a little bit over what we want to what's important for us to see. We go down here, and we look at the gamma ray energies. We have values of 300 Weisskopf units. So these are very big. So let's say a unit of 1 is for a single particle excitation where you have no collectivity. For this fellow, if we go down here, for this fellow, for instance, if we go down to the gammas, levels, and we go to the gammas right here. So you see 160 Weisskopf unit as compared to 1 Weisskopf unit, which will happen for an ideal single particle excitation from here to here, right? So this large number, 160 versus 1, is an effect of having the nucleus doing the same thing, as we can see here, right? As we can see here, the nucleus is doing the same thing because the wave function of the 6 plus look very similar to the wave function of the 8 plus, the wave function of the 4 plus, the 2 plus, and 0 plus. Right? If the nucleus suddenly does something else, then these transition probabilities will be not so big, actually. But as it is the case of these two particles, we broke a pair of particles. Now the nucleus, this angular momentum, will couple there. Now the nucleus is not rotating around this axis. It's rotating around this axis. It's rotating like this. And I'll tell you why tomorrow. So as of today, we have introduced the collective motion. We have deduced the energy spectrum. We know that these are all decaying by E2 transitions. And we know how to predict what the excitation of the excitation energies will be for a rotor, which is nicely deformed, as we see right here, right? This nice deformation makes the nucleus rotate. And again, the energy of rotation is much smaller than whatever we have for a vibration, and generally for a single particle excitation. Okay, so these are the things that we need to know. And today's lecture, again, there's a lot of information, but we started from something very similar, right? This was our single particle excitations. Then we have our harmonic oscillator, with equidistant gamma ray energies. We know that this, obviously the energy of the 4 to the 2 must be equal to 2, right? Because these guys have the same energy. So basically this is 1, this is 2, 2 over 1 is 2. And this is how we characterize. We see when we do an experiment and we excite the nucleus, we see this guy is vibrating. This is something spectacular. You're not seeing the little nucleus 10 to the minus 15 meters, one few Fermi apart, we know what it's doing. You know, this is something, you know, incredible. It's out of, it's really, really beautiful. And then we use the properties of the rigid rotor, that this distance, whatever is the distance, is always constant. So V is equal to 0. And for that, the total energy of the rigid rotor is equal to this one, which we quantize, and we reach this point. And this is the energy, and this is the energy that we have been, the eigenvalues that we have been using in the rest of the lecture. We calculated for the 2, for the 4, for the 6, and we see that there's a nice agreement between rotors and these nuclei, which are very well deformed. Even better agreement between in samarium and 56, where the energy is lower. So the rotational degree of freedom is enhanced. You can rotate better because we have a larger, a more deformed nucleus, right? And we have concluded stating, you know, that we know how a spectrum will look like, and that these transitions coming down, these gamma ray transitions, will be very, very fast